Hello, everyone. Welcome back. Today, we're going to continue to talk about permutations. So, just a reminder last time, what did we talk about? We learned about factorial notation. We also learned about some basic permutations, right? So, if you haven't watched that lesson or if you're unfamiliar, if you were confused, make sure that you get that sorted out before we move on to this next one because you're going to need what we learned last time in order to be successful with this lesson today. Okay. So let's talk about permutations. So just a reminder, what is a permutation? A permutation is an arrangement of n distinct items, or could be letters or people or anything like that, that are all arranged in a particular order, right? So if I wanted to figure out how many ways 10 people lined up at the bus stop, for example, that would be a permutation because I care who's first, who's second, who's third, and who's last, and everybody in the middle, right? I actually care about the order. Order matters. Okay. So I want to talk about various other kinds of permutations that we didn't do last time. If n items are arranged with r possible positions, then there is npr or pnr in this case, ways of doing so. And keep in mind last time we said n factorial was npn, and this was a fact I mentioned but kind of glossed over because it wasn't really that relevant then, but now we can kind of make sense of this, right? That n factorial is going to be the same thing as, we start with n and then we do, n multiplication types of it. Whereas here, let's say we have npr, or p and then in brackets n comma r. I prefer this one, by the way. This one reminds me too much of, multivariable probability, that sort of stuff. So I prefer this way, but either one is completely fine. Um, Here we have n factorial over n minus r factorial. Now, before I get into questions about this, I'm going to go over, well, why is that, right? We explained earlier in the last time why are there n factorial ways of arranging items in that many, positions, right? N items in n positions. But now I want to talk about what if there's a different number of positions. So what if, for example, there's 10 people who are, let's say 10 people who are doing a swimming race, right? They're swimming, they're trying to win. And only the first three people get prizes. Maybe first place gets $100, second place gets $50, and third place gets 25, and everybody else gets nothing. And so, as far as you're concerned, it doesn't matter if you're fourth, fifth, sixth, seventh, eighth, ninth, or 10th, because everyone's competing for those top three positions. And not only for those top three positions, but it does matter which order the positions are in, right? Because although it would be nice to win anything, of course, everyone would rather have $100 than $25, I would imagine, right? And so not only do we care whether or not we get in the top three, but we care about which order we're in the top three. What we don't care about is if we don't place at all, it doesn't really matter if we came in fourth, fifth, sixth, seventh, eighth, ninth, or 10th in terms of how the prizes are distributed. Perhaps we'd rather come in fourth or fifth because it means, we did beat some people. We still, did a pretty good job. But in terms of what prize we'll win, it's the same outcome, right? Fourth to 10th all gets the same prize. So let's think about that. How many different people could get first place in that example that I just gave? Well, 10 possible people, right? There's 10 swimmers. Any one of them could get first place. Okay. Now, how many of them could get second place? Well, someone's already got first place. Someone already touched the wall and said, I got first place. I win. How many people are left still swimming? Well, there's 9 people still swimming. One of those 9 people is going to get second place. The person who got first place can't also get second place. And then, okay, first and second are chosen. Everyone keeps swimming, and then someone, bam, touches it and gets third place. So there's 8 possibilities for how many people get third place. And then the other 7, we don't actually care in terms of how the prizes are being distributed, who comes in fourth, fifth, sixth, seventh, eighth, ninth, or last. So there we have it. We have 10 times 9 times 8, right, in that example that I just gave. So let's talk about that a little bit in comparison to, how does that relate to this equation? Well, let's say we had 10p3, right, or we had 10 people in 3 possible positions. If I write this out, that's 10 factorial over 10 minus 3 factorial, which is 7 factorial, which is 10 times 9 times 8 times 7 factorial over 7 factorial, which guess what? That's 10 times 9 times 8. That's exactly what we just said over here, right? So essentially what this equation does is it says, okay, we're going to do 10 factorial or whatever factorial of the number of items that we want in our arranged order. And then we're going to divide that by, the factorial of people that we don't care what order they get into. Those last 7 people, we don't actually care what order they're in terms of the prizes. So we divide by that number. And so we only have those first 3. And so that's why this equation is the way it is. So that's something I wanted to quickly discuss with an example of, let's think logically about how would we figure this out, which we did, and we came up with these numbers, and then we can see how our logic fits in over here with when we actually plug it into what they're telling us it should be, right? So this is the general equation, and this general equation makes complete sense given our intuition over here about, well, how many people could possibly get first place? Okay, how many people could get second? Okay, how many people can get third? We stop there. Very good. All right, so now I'm going to give some examples. For these examples, now that we understand how the equation works, I know most students would prefer to just plug something into an equation as opposed to think about it intuitively, so I will be using this equation, but I also think it's somewhat important to understand why an equation is the way it is, because if you understand why that's the equation, not only will you have a stronger knowledge understanding of the topics, but also if you don't get a formula sheet on your, on a test or something, and you forget a formula, it's like, oh, I understand that formula, and you can come up with that formula. The formula comes back to you. Whereas if you have no idea why the formula was there, you just tried to memorize it and then forgot, well, good luck, right? It's not going to work out so well, right? And so understanding the formulas gets us to be able to, even if we haven't memorized them, makes them come back. I'll be honest, I do not have this formula memorized. However, I would be able to figure out this formula if given the opportunity to do so, because this formula makes sense given the situation. All right, so that said, let's move on to example 1. Example 1 says, the lock on a school locker goes from 0 to 59. How many different 3-number combinations could there be, assuming the same number could not be used twice? Well, let's think about that. So we would have 59 P3, right? Which is 59 factorial over 59 minus 3 factorial, right? So 59 minus 3 is 56, right? So this is the same as 59 times 58 times 57 times 56 factorial over 56 factorial. We cancel those, and we just have 59 times 58 times 57. And the answer to that is 195,054. So that's a lot of combinations. So odds are no one's going to be breaking into our locker anytime soon, which is good. So there we have it. Another way we could have done this, if you do prefer the intuitive way, then in that case we could just say, well, how many possibilities are there for the first locker number? Well, there's 59 possibilities, 59 different numbers that it could be. Oh wait, it says 0 up to 59. So is 0 a possibility? You know what? I've done this wrong. I think then there's 60 numbers because 0 counts as a number. My apologies. Let's go back. It would be 60. And then this would be different as well. This would be 57. So actually, my apologies. This would be slightly different here than what I was saying. So this would just be 60 times 59 times 58 times 57 factorial over 57 factorial. I'm going to leave that in there because I want to make a point about 0 also being a number, and I had forgotten that. I was thinking, oh, it's just numbers 1 to 59, which is 59 numbers, but 0 to 59 is actually 60 numbers. So my apologies for that. But yeah, there we go. So it's actually slightly better than I thought. It's 205, 320, right? So over 200,000 different combinations, right? Because the first number, right? The first number has 60 possibilities. It could be 0, 1, 2, 3, 4, anything between those numbers and 59. And then the second number, there's only 59 possibilities because whichever number we chose for the first number can't be chosen again. And then for the third number, there's only 58 possibilities because whatever the first two numbers are, we can't repeat again, right? And so it's a different scenario. If we could repeat numbers, then we'd be doing a whole different equation here. We wouldn't be using this formula or this method. However, in this case, because the same number can't be used twice, we are able to do it this way. Or same with when there's people standing in a line, right? We can't choose, one person can't stand in two places at once. I can't be both in the second position in the line and in the 10th position in the line. It just doesn't work like that. And so because we're not able to repeat, we're able to use this method. But yeah, long story short, there are 205,320 ways that we could possibly have a combination at our school for the locker in this scenario when we have numbers from 0 to 59, and any number of those could be chosen as long as we just don't choose the same number twice. Let's do another example. Example 2 asks, with the letters A, B, C, D, and E, how many three-letter words could you create? So the reason words is in quotations is because it doesn't actually have to be real words. They're just saying any form of three letters in any order. So I could say, oh, well, A, D, E is a word, even though I don't think that's a real word. Or C, B, E, I could say, oh, that's a real word, right? Even though, it's probably not a real word. I don't think that's a real word as far as I know. So basically, any combinations of three letters, that we could choose, and then also, how many words we could create with that. So let's talk about that. How would we figure out this one? Well, we would say that there's 5 letters, and we're going to choose 3 of the letters, and we want to also know the order of them. The order of them matters because we might choose the same 3 letters but have multiple different permutations, right? For every 3 letters we choose, there's actually going to be 6 different ways we could arrange those letters, which is interesting. So let's do that. We're going to have 5 factorial over 5 minus 3 factorial, which is 5 factorial over 2 factorial, which is 5 times 4 times 3 times 2 factorial over 2 factorial, which is 20 times 3, 60, right? Or we could also just figure out that it's 5 times 4 times 3 by saying, well, for the first letter, there's 5 possibilities. Then for the second letter, there's going to be 4 left. And then the third letter, there's going to be 3 possibilities left. And so that's another way we could think about this. Very good. All right, and this one, same thing. We're assuming that we can't choose the same letter twice. We're assuming each letter can only be selected once. Otherwise, there would be more possibilities than 60 if that was the case. Good. All right, let's try 3 and 4. And actually, in the next part of this, we'll talk about permutations where we actually do have to, have some repetition potentially, because that's a whole different method that we'll talk about later. But for now, we're going to assume we're not repeating anything. This one says, if you are going to have a 4-digit house code where 0 is not used and a number cannot be used twice, how many possible addresses numbers could you have? Okay, so we can't use 0 anywhere in our 4-digit house number, and no number can be used twice. How many possible addresses could we have? Okay, well, this one, let's see. For this one, we have how many digits? Well, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, because 0 is not used, so we have 9 possibilities for our house number. And we're going to be choosing 4 of those digits. We're going to choose 4 of them, and also we're going to make sure that those 4 could be arranged in any order. So permutation 4. So actually, I shouldn't be saying 9 choose 4 because that's actually something different we'll learn later. I should be saying 9 permutation 4 because the order does matter, right? If I have a house number 1, 2, 3, 4, that's different from a house number of 4, 3, 2, 1. Okay, so let's do it. We have 9 times 8 times, actually, let's write down 9 factorial over 9 minus 4 factorial first, like that. Then we have 9 factorial over 5 factorial, which is 9 times 8 times 7 times 6 times 5 factorial, over 5 factorial. Those cancel. So we just have 9 times 8 times 7 times 6. 9 times 8 times 7 times 6 is 3024. So therefore, we could have 3024 different numbers possibly on our house. Good. All right, so I think you guys probably got the idea by now. So if you'd like to try number 4 on your own, feel free to do that. If not, that's all right too. But a lot of these, they just follow the same pattern, which is kind of the nice thing about them. Okay, example 4 says, in how many ways can a basketball team of 13 take a team picture lining up from left to right if the shortest player cannot be on the far left and the tallest player cannot be on the far right at the same time? Okay, so let's think about that. We have a basketball team of 13 lining up from left to right, right? So our immediate thought would be, oh, well, 13 factorial. There's 13 factorial ways, but we do have a restriction here, which I want to talk about a little bit as to what the restriction means to us. Okay, so what might that restriction actually mean to us? That the shortest player can't be on the far left, and the tallest player cannot be on the far right at the same time. All right, so for this one, we can say, well, we're going to take the 13 factorial ways, which is all the ways, and then we're going to subtract off all of the different ways where the first player, is that shortest player, and then the tallest player is that last player. So what are the total number of ways the team can line up if the shortest person is at the left and the tallest person is at the right? Well, there's 11 factorial ways that could happen, right? And now why is that? Let's talk about why that is, because we have, all these different ones here. If we have the shortest person here and the tallest person here, and then we have all these 11 spaces, however many that is, right? 11 factorial in the middle, that's how many ways we could rearrange those remaining players with the players there. So basically we're saying here's 13 factorial, that's all the ways they could do this, minus 11 factorial, which is all the ways that they could do it with, if we let the restriction, if the restriction was true, right? And that's a common way we'll do things when we do have restrictions is we'll say, well, let's take the total number, then let's subtract off the things that cannot be true, and then we're left with whatever is true in the situation or whatever is allowed. Now this one, actually, I would accept this answer. You can just leave it as 13 minus 11 factorial, or you could say, well, this is the same as 6.22 times 10 to the power of 9 minus 3.99 times 10 to the power of 7, which means that there is 6.18 times 10 to the 9 ways that this could occur. Very good. Very good. But when we have huge numbers like this, you can see why evaluating is not really most people's primary concern, if we're being honest, because, it's, it's not really people's primary concern isn't really evaluating. Very good. All right, well, that's going to be it for today. Next day, what we're going to do is we're going to talk about permutations with some identical terms. So we have another equation for that, and we're going to talk about why that equation is the way it is. And then we're going to do some examples in order to help us out with that. So I hope everyone has a good rest of your day, and we'll see you next day for that one. Bye, everyone.